Here we are in another polynomial equation to be solved, but this time, again, find all solutions, not just find the real solutions. And this time we have a cubic expression in our equation as opposed to the quadratics that we've been seeing. We've been seeing x to the second power using the quadratic formula, but actually we will use the quadratic formula here. And you might be thinking, oh no, crazy lady, it's not a quadratic. Why would I use quadratic formula? Well, you will see, won't you? Now, if you choose to solve this by adding 8, dividing by 27, finding the cube root of both sides, you will find exactly one solution. However, we know that the greatest power or the degree of this equation is 3, and that means there will be 3 solutions to this equation. And if we solve the way I first mentioned, we'll only get one answer. So something's not good. If you only have 1 and you should have 3, we're missing 2. Imaginary and irrational solutions do come in pairs, and they also come from, quite often, the quadratic formula. So is there a way that a quadratic should be involved in the solving of this? I'm glad you asked. Of course. This right here is the difference of 2 perfect cubes. There is no greatest common factor. We always look for those first, right? But there isn't one, so we can just put on our X-ray vision cubing glasses to figure out what's being cubed to make this cute little equation. Well, over here we're cubing 3x, and over here we're cubing 2. Careful that we don't get sloppy, because sometimes we mess up. People are putting 9s and 4s and being all weird. Don't do that. So X-ray vision, here we see what we got. 3x is being cubed, 2 is being cubed, difference right there. If you need help on how to factor the sum and difference of cubes, I have a full-blown lesson video on the playlist of factoring methods, and we go through my silly technique, which has been working great because I think my students are amazing at factoring these. Aside from the occasional sign slip up in that opposite spot, really, I have to say I'm quite impressed with you guys. All right, so what do? Over here, you should know it's 3x minus 2, and the quadratic factor is 9x squared plus 6x. That's my dog again. Oh my gosh, he is in rare form tonight, let me tell you. 9x squared plus 6x plus 4. And this is, I promise, if the problem was asking us to just factor, you would be done. But it's an equation, not an expression. So expressions, you might stop. And that's going to be a quadratic that's prime, and you can't go further. However, it's an equation, and the directions are to solve or find all solutions. So what do we do when we can't factor a quadratic? We use our favorite friend, the quadratic formula. So let's get into all of this. Now, this here is a linear factor. No funny business here. We take our linear factor. We don't try to be too cool for school by just jumping to the answer, because this is a case where a lot of you mess up. So we're going to write it out. Zero product properties happening. We're setting this equal to 0. 3x is equal to 2. Add the 2 over. And divide by 3, x equals 2/3. You may want to show more work. This right here is a real solution, and that is the answer you would have gotten if you just solved by adding 8, divide by 27, cube root of both sides, yada yada. Now, let's go to the quadratic. X equals, yeah, that's right, I'm going to write the formula again. Negative b plus minus the square root of, do you know it? Can you finish it without me? Go. Do it. I dare you. B squared minus 4ac all over 2a. Okay, now we fill in. A is 9, B is 6, and C is 4. X equals negative 6 plus minus the square root. 6 squared minus 4a C all over 2a, which is 2 times 9. We're going to continue. Up there. X equals negative 6 plus minus the square root. Now we did see an example that was pretty similar to this one with the numbers set up underneath. So I'm going to switch it up this time. I'm going to do it like I did the previous example, where I'm going to show you my little workaround where I'll never actually have to multiply these and actually subtract them, because I'm going to do my little cheap trick over here. So let's see what that looks like. 6 squared is 6 times 6. And 6 times 6, well, each 6 is 2 and 3. So we have 2, 2, 3, 3 minus 4, 9, 4, 2, 2, 2, 2, 3, 3. All over 18. Okay, we're going to factor, right? What does this have in common with this? Well, 2, 2, 3, 3, 2, 2, 3, 3. All right. What's left if I pull that out, and not all the way out of the radical, we're just factoring what's inside of my radical, okay? That means I got x equals negative 6 plus minus the square root. 2, 2, 3, 3, 4, and 9. Perfect squares. Love them. What's left here? 1. I explained this more in the previous example, so you might want to check that out if you're like, what the heck are you doing right now? Minus what's left over here, 2 times 2, which is 4. All over 18. Now, 1 minus 4. That right there is going to be negative 3. This and this takes a pair to make a square. X equals negative 6 plus minus 2 comes out, 3 comes out. Radical 1 minus 4 is left. And what is that? We said it's negative 3 all over, left a little room there on purpose, 18. The negative can come out. It's going to turn into a positive because that negative comes on out and turns into our imaginary unit I. X equals negative 6 plus and minus 6i square root 3 all over 18. Oh boy. There we go. Now, time for the purple pretzel. What is it that I can reduce from those ovals? Well, a 6. So, where does, oh my gosh, he's so crazy today. Where are we now? I'm just going to scooch this up a bit. Sorry, it's a little squishy. X equals, take a 6 out, and a 6 out. Knock out a 6 from everybody. What's left behind? Negative 1 plus minus I root 3. 18 divided by 6, it's 3. Okay? Some of you don't know that. Some of you think it's 2. 6 times 2 is 12. We got to work on that. Okay? Okay. So, knocking out that 6, we get 3. And here we have 2 imaginary or complex solutions. Okay? And here, 1 real. In total, how many answers do we have? We have 3 answers. What's the degree of this equation? It's a 3. So imaginaries, again, always come in pairs. Got 2 of them, and we got that 1 real answer. If you instead wanted to do this, or maybe you already did, do this by the more traditional approach, you would have gotten a 36 minus 144. Then that would give you a negative 108 underneath your radical. I'm just going to write that over here, negative 108. Fun fact. Fun fact is, if you are solving the quadratic you create from a sum or difference of cubes example, you will always be able to divide the radicand or the discriminant, the thing underneath that radical, you'll always be able to divide it by 3. So if you're really not sure where to even begin, it's an odd number, maybe it's not divisible by 5, and you're like, hey, where do I even start? 3. Start with 3. You will always be able to get a 3 out of it, okay? I promise. And it'll be 3 times some perfect square, okay? So hope this was helpful. I hope you feel like a genius. If you're doing great, thumbs up. If you hate this, thumbs down. Click the video if you need the next example. Go to the playlist if you're looking for something else. I do have another one of these with 64 and 343 in it, so it'll be a great opportunity to see why my silly little trick can come in really handy, because those numbers are much less adorable than maybe the one in the last example. This one would be a little gross, -108. That's a little annoying, right? All right, well, adios.